Hi guys, I'm John Herbst, and today I'm going to be talking to you about how we can approximate a function they don't really know that much about, besides some features of the function at an initial starting point. So let's take a look. Alright, so what would you say is the best approximation for a function if all I told you was that at the initial time, 0, the function had a value of 2? Well, you might think that, for example, if I told you to guess what the function was at 1, that you would guess 2. And that's exactly right. If we have no other information about the function, then our best guess is that it's a constant function, and we should guess 2 at every value of x. So our first approximation for that function, if we don't know anything besides the initial value, should be that initial value. Now, we are assuming that the function doesn't change at all. So what would be our best guess if we found out some more information about the function and knew that the function was 2 at 0 and also had a slope at 0 of 1? So the first derivative of the function at 0 is 1. Well, just like last time we assumed that the function didn't change, this time we'll assume that the derivative doesn't change. So we want some function that has 2 as its value at 0 and a first derivative of 1 at 0. And so we'll look here at this candidate function of h of x, which is our first approximation, and then some added term, and in this case we're using 1x, which is the derivative of the function times x. So looking at that, h of x is just a constant. So if we look at the value of this at x is 0, h of x is going to be 2, and 1 times x is going to be 0. So that's preserved. Now if we look at the first derivative, this derivative of this constant term is 0, and the derivative of this term is 1, which is what we wanted it to match. So this right here, this line of 1x plus 2 is our best guess at the function given what we know, which is just that starting point and the starting derivative. Now, suppose we find out some more about the function. We know the second derivative of the function is 2. So just like the first time we assumed the function was constant, this second time we assumed the derivative was constant. Well, now we just found out that it's not. The derivative is changing too. So instead of a line, we're going to have something that doesn't have constant slope. So we're going to take a look at an approximation where we're adding a term. So q of x is our last approximation, and we know that function evaluated at 0 was 2, and we look at this second term evaluated at 0, that's going to be 0, so the sum of them is going to be 2. So it preserves, as you can see on the graph, that this approximation matches the function at 0, because f of 0 is 2. Looking at the first derivative, we know the first derivative of this was 1 at 0, and the first derivative of this would be, let me type it out for you. You would have 2 times 2x divided by 2, which is going to equal 2x. And if x is 0, then this is equal to 2 times 0, which is 0. So the total first derivative for this approximation would be 1, which is what we hoped. Because we're trying to approximate that first function, we know that first function has a derivative of 1 when x is 0. Now if we look at the second derivative, it would be the derivative of this function. So what's the derivative of 2x? It's 2. And what's the second derivative? What's the derivative of the second derivative of q of x? Well, this is derivative of this is 0, derivative of this is 1, and the derivative of that constant 1 is 0. So this derivative of this total qx here is going to be 0, and the derivative of this term is going to be 2. So the second derivative of this function is 2 at x is 0, and that matches what we hoped. So that's a good approximation. It's actually our best approximation given what we know about the function at 0. Now assuming we find out some more about this function, we find out that this second derivative wasn't constant either. It's also changing. We find out that the third derivative of the function, which is the derivative of the second derivative, is 6. So we're going to try and come up with some approximation that has all of these things true about it. So here's what we're going to look at. R of x is the previous function. So R of 0, as we saw, was 2. And 6x cubed, this term, over 6, evaluated at 0 is 0. So that total function is going to be 2. The first derivative, this one's going to still have an x term in it. So that's going to be 0. And the first derivative of this, as we saw, is going to be 1. So the first derivative of this function is going to be 1. The second derivative, this is still going to have an x term in it. So that's going to be 0. And the second derivative of this, as we saw, was 2. So the second derivative of this function is still going to be 2. And then the third derivative, let's take a look. We can see that the second derivative of this function is 2. So the third derivative of that's going to be 0 because it's a constant. So this part of the function has a third derivative of 0. And this term, let's see what we get. The first derivative is going to be 6 times 3 is 18. Divided by 6 is 3, x squared. And then the derivative of that is going to be 3 times 2, so 6x. And then the third derivative is the derivative of that is going to be 6, which matches what we wanted the third derivative of the function to be. And so here's our fourth approximation, and it looks like this. So now we're going to take a look. We could have more information about the function. We could find out that there's a fourth derivative or a fifth derivative and so on. But let's assume we don't find anything more about the function. We want to see how closely it matches. So here's the actual function, and you can see that it actually perfectly overlaps our fourth approximation that we did. It doesn't have to be that way. I mean, our original function could be something different so that this fourth approximation would be not that close. But if we look at what that original function was, it's x cubed, and it is the highest degree, and so it actually overlaps because there aren't any more terms of the function.